Welcome to lecture number 3, today with a slightly reduced live audience here in Goslar due to some, I don't know, let's call it temporary lecture plan changes that caused some logistics challenges to get out of bed or out of your own home and getting back to the lecture room. But we'll still try our best, and I was told that next week we should have a super motivated live audience once again. Today, we're finally going to talk about climate change, or more commonly known as global warming. But before we get to climate change, I will try to get my pointer working. We'll talk a little bit about your homework from last week. So I have 2 reference points in the audience that I can ask, how many days of waste did you manage to fit? First of all, what roughly the size of your jar or containment that you used? Ladies first. But I don't know, 30, 40 centimeters? One bigger than an A4 paper? A4 is 30 centimeters. An A4 paper is 30 centimeters. Almost, okay?
I got a liter box.
Yeah.
It's still not full.
It's still not full. That's not bad. How many days did you last? 6 days. So, okay. We have something that's about 30 centimeters in height for a jar and a 1 liter box that is still not full, which is not bad, honestly. Unfortunately, this time we did not receive pictures. Last semester, we received quite a few images that also helped us a little bit to figure out, okay, what type of trash is most commonly accumulating in your household, but also is there like something like not once in a lifetime, but unusual trash within that system. So if I buy a new notebook, that notebook comes pre-packaged, and I don't buy a new notebook every day or every week, at least not on a regular schedule. So that needs to be accounted for. But that was quite interesting last year. So if you still have some images, don't hesitate to share and send them to us. But in general, 6 days and not full yet is really a good result. Those are the results that we received so far. It might not be the most up-to-date result because we had to get them into the slides. So we didn't do that 5 minutes before the lecture because we're well-prepared lecturers. So most of you did manage to get it to a day or more. There were some who even said still not full, even so 4. But in general, there were some people missing. I know that there are more people in this course than those that we have here on the slides, because that's like 2, 5, 7, 9, 13, if I'm not mistaken now. We have more than 13 people participating, but still, at least we got some feedback. Still not full is, of course, like very nice. 1 or 2 days indicates that you either have a very, very small jar or a lot of trash. And I don't really want to now create categories of bad or good, saying it's really bad that you didn't make it like until 1 day, or it's really good that your jar is still not full. Obviously, it's good if you don't create a lot of trash, but I don't want to really make this now a game where we blame someone, because there could also be very genuine reasons why you're accumulating a lot of trash. For example, when we first did this homework, Anand and myself, we also participated in this homework, and then we collected our trash for as long as possible. And in my case, I didn't really last very long, even though I'm trying to really minimize how much trash and waste accumulates in our household. But there is a concept called food sharing that you will learn about in one of the MOOC contents, or might have heard before. And I'm very active in that community, and that means that I'm grabbing and collecting a lot of leftover food from supermarkets before they throw it away, which in turn results in me having a lot of the packaging material from those supermarkets in my household. So it's not really the waste that I'm creating myself and causing myself, but it's still like ended up in that jar, so my jar didn't last very long. So there can be different reasons why a lot of waste ends up at your place. That's why I don't really like to say, okay, good or bad. The point of this exercise was to give you a little bit of a feeling, okay, how much waste am I creating by default, even if I like even if you say, okay, look, I tried really hard to minimize it, then you still like, how far did I get? Or if you just did it because we asked you to do so, and you didn't really take any precautions, you did not try to minimize, just to get you a feeling like how much is accumulating just for you as students. And you are not among the worst polluters on this planet. You are actually among those people who have a very limited budget, at least most of you. Therefore, you do not accumulate a lot of nonsense stuff every week or month or so. That usually gets more and more the more income you have. So my point being giving you an idea of how much that is, and thanks a lot for participating. There is one slide missing that is a little bit unfortunate, but we'll make sure that it's uploaded. There is one slide in between here where I'm linking you to a YouTube video where they had a family of, I think, 2 adults and, if I'm not mistaken, 3 children. And they were also essentially doing pretty much the same challenge as you are doing, just on a more extreme level. So they really try to avoid all types of waste or trash. If they had any trash, they're trying to repurpose it. So if I have a plastic container, of course, I can put a label trash on the plastic container, or don't use it again, or I find another way of using that plastic container to store other stuff in it, then it has suddenly a purpose again. So you're upgrading, upcycling what you have as trash. And otherwise, they're trying to just avoid any type of waste. So don't buy packaged stuff and so on and so on. And they have a jar, I would say, about that size. And question for you, how much or how long do you think those people lasted for a family of 2 adults, and if I'm not mistaken, 3 children? How long did they manage to do this on an obviously very extreme level, because they made it, like, they ended up on YouTube, so you don't do that, or you don't end up on YouTube if you lasted for a day or so. So guesses from the audience? 2 weeks is the first guess. 1 week is the next guess. Any guesses from the online audience? Probably good now that you all cannot really just like briefly look up the video. I forgot, or that the slide didn't, for whatever reason, not make it into the live lecture set. So there's a little bit of input. 2 weeks, another week, so 3 weeks. Very similar to what we have heard from the audience. 3, 2, 1. You're all very, very far off. When they recorded the videos, they were 2 years into that challenge, and the glass wasn't even full. So obviously, like, very, very extreme example, and you also have to take it with a grain of salt. They ended up in a YouTube video that probably didn't make them rich, but maybe had some financial incentive. I don't know, blah, blah, you get the idea. But the point was, if you look at the video, if you watch the video, which was quite entertaining, even if you take it with a grain of salt, there are quite some. There is the video, thank you very much. I cannot show it to you now because then we get copyright issues with the recorded video. There are quite some nice ideas and thoughts on how to minimize and reduce the amount of waste that you're accumulating. Some of them might be applicable to you, others might be more complicated, but just going through life more mindful with respect to how much waste you're accumulating and can I avoid that waste, could be like one of those really easy steps that you can do on a day-to-day routine. Like, it's not going to save this planet, that you as a single individual, even if we take all the 20 people in this course, if you all like 20 times do that, it's not going to save the planet, but it's also not going to make it worse. So please do so. And now we're going to get to climate change or global warming. And before we start with the fun part, first gonna get some foundations straight, so the basics with some definitions. And we first start with this very shitty pointer. I hate it. And talk about the difference between weather conditions, and climate. So, great questions to the audience. How would you define weather? What's weather? Not just pointing outside and telling me the rain outside is weather, which is true, but more abstract, please.
It's raining or the sunshine, but only day-wise, or like maybe also in a week, but not that long.
Okay, so just repeating for the microphone to pick it up. So something like sun, rain, fog, or whatever, but in a short temporal time scale. So a day, or maybe, as you said, for a week. Okay. Another thoughts from the other part of the audience?
Yeah, weather is actually what is happening right now.
Okay, so weather is happening. What is what is happening right now? Was the second point, and I would say you're not that far off. So because it already says it's a current thing. So weather is, according to that definition from the University Institute, weather is a combination of the current meteorological components, e.g. temperature, wind direction, speed, amount and type of precipitation, sunshine hours, and so on and so on. There are many components. The weather is defining a short time period up to several days. So you intuitively got it right, like what's happening right now. You could also say like this is like on a local level for the sake of, or like for our perception. Of course, the weather at other places also exists, but for us, like what we usually perceive as the weather is what's outside happening right now. A related concept that is also quite relevant here is so-called weather conditions. The weather condition is the regional weather during a defined time period. So weather right now, and weather condition is now regional, to localized geographical position, and for a predefined time period, from 1 up to several weeks. So weather, short time period up to several days, and now we're talking about 1 week to several weeks. Weather conditions describing typical weather phenomena, such as a series of thunderstorms in hot summer, foggy month in autumn, or other weather conditions which are typical for a specific region and or season. So for Clausthal and Goslar, you could say windy and rainy at all time. It took me months working in Clausthal before I had the first day where it did not rain. So this could fall under this category with some limitations, obviously. So weather and weather conditions, first relevant building components, so that we do not confuse them with what is climate. Because climate now is describing the long term, at least 30 years, and average weather conditions for a specific region. So for example, maritime climate, cold and dry desert climate, tropical climate. So weather, short time period up to several days. Weather conditions, regional weather during a defined time period, usually for some weeks. And then climate, something where we talk about at least 30 years. And even though this seems to be rather intuitive, it is something that a lot of people don't really get straight when they are talking about those differences. I'm not sure if you have maybe seen this quite famous video from the US Senate or Congress, I don't know, where there was a Republican who had a ball of snow in his hand and said, look, there's snow outside, so climate change cannot be real. Given those definitions that we just talked about, there is an obvious problem with his definition or with his claim that climate change isn't real, because the fact that there's snow outside doesn't really diffuse or refute the fact that climate change might exist. And what's now changing climate? You could just say, okay, yeah, we had the climate for that time and now it's changing, that's climate change. But maybe in slightly more detailed context, climate change is a long-term change in the average weather patterns that have come to define Earth's local, regional, and global climates. These changes have a broad range of observed effects that are synonymous with the term. So we have the long-term climate for at least 30 years time period, and this is now changing. and that is where we get climate change. We're gonna use, or I'm probably gonna use climate change and global warming synonymously in this lecture, which is a simplification and not 100% perfectly correct, but global warming as one of the major drivers that is changing our climate, you get to understand what I mean. I'm trying to use the perfect and absolutely correct term whenever appropriate, but if I don't do that, because sometimes I'm just getting into talking, please don't cancel me, and please give me a little bit of space, and you know what I mean. So, weather conditions, climate, and changing climate. 4 important definitions to have a proper discussion about that topic. And it could also be rather relevant for the examination, because those are those terms that I would like to talk to you about in the examination to really get an understanding, okay, do you now know what this university is concerned with? And this is one of the very much foundations. Good. A major component or part of global warming, and therefore also part of climate change, is the so-called greenhouse effect. So greenhouse, or in German Gewächshaus, you might know that concept. You build something like a glass house and it gets quite warm in there, so you can use it to start the gardening season very early, and you can also use it to extend the gardening season, and you can also use it to, for example, grow plants here in Germany that are not quite as typical here. So it's very good for tomatoes, for certain types of spinach and whatever, so that's something that doesn't really live here, but in this greenhouse that gets warm through sun and to via sun's input, and you can use it then to grow some stuff in there. And pretty much the same effect is exhibited or can be observed in our atmosphere. So we have the sun shining on our planet, and then we have an atmosphere on our planet. And where we have the sun shines getting to our planet, some of the radiation is absorbed, for example, by the ocean or by the land masses. Others is reflected, for example, by our ice or other types, straight back into the atmosphere. And some of this is going straight back. Other parts are then trapped in the atmosphere by bouncing, for example, into molecules like CO2, but also methane and other so-called greenhouse gases, GHGs. And they make sure, or they lead to the effect that the radiation doesn't leave the atmosphere again, but rather gets stuck in there, and that causes our atmosphere to heat. So you have pretty much the same effect as you would have in a greenhouse, where you have a glass, sunshine comes in, it goes through the glass, and then it gets stuck in that greenhouse. The same happens on a simplified manner here with our atmosphere. So sun gets to our atmosphere, it gets stuck in there, and this is how our planet warms in very, very simplified terms. And I will explain a lot of concepts today, but I will try to simplify them for the sake of this discussion. Those are the basics of climate change. This is not a meteorological advanced PhD study group on global warming. This is the simplified basics of climate change and global warming. So this was the intuitive explanation. What's global warming now on paper in a more precise definition? Global warming is the long-term heating of Earth's climate system observed since the pre-industrial period, so between 1850 and 1900, due to human activities, primarily fossil fuel burning, which increases heat-trapping greenhouse gas levels in the Earth's atmosphere. So in short, how did burning of fossil fuels cause more greenhouse gases being trapped in the atmosphere and thereby contributing to a warming of our atmosphere? The term is frequently used interchangeably with the term climate change. Already told you that. Though the latter refers to both human and naturally produced warming and the effects it has on our planet. It is most commonly measured as the average increase in Earth's global surface temperature. So how much did the global surface temperature of our planet increase compared to the pre-industrial period, so 1850 to 1900? So how much warmer is it now on average compared to something like 150 to 200 years ago? And you might have seen Or you might have heard, because we already talked about that in the previous lectures, that we have always this goal of limiting global warming to 1.5 degree Celsius above pre-industrial average. This is essentially where this is where those two things come together. What you might also have read in the past few days is that on the 17th of November 2023, so last Friday, we had the first day where, for the first time, where the global average temperature that crossed the 2 degree threshold. Just for a day. It doesn't mean that we have reached 2 degrees global warming by now, but it's the first time that we measured, that we verified that we hit that threshold since we existed. So not really perfect, great news for that 2 degree target that we're now moving towards that. We already discussed that the 1.5 degree global warming goal is more or less dead. Even if we stop all greenhouse gas emissions today, we still would struggle to get to that goal. So 2 degrees is essentially the next landmark that that we have to deal with. So this figure has the first self-study star that I talked about in the org lecture. So there are some slides with this self-study star that I will only either not scratch at all in the lecture or really briefly touch. This is one of those that I will briefly touch. First of all, there's quite a lot of content in there, a lot of text, and it's quite hard to probably read from the perspective of the audience. The main gist of that figure, what it's supposed to illustrate, which you then can study yourself in more detail using the text and the additional information there, is that the Earth energy budget can roughly, what that contributes to global warming can be roughly divided into 2 major components. So first, we have incoming solar radiation from the sun that hits our planet. Second part that we also have is so-called infrared radiation that is emitted by our surface of our planet. Those are the major 2 components that cause heat in our atmosphere and our ecosystem. So from that from this incoming solar radiation, some parts are straight reflected by clouds in the atmosphere. So there is like an estimation of, what was it? I have to look up the units for this. So, but like a larger portion is already straight reflected by the atmosphere and the clouds. So parts go straight back. Then there's other parts reflected by the surface, and all of this together is roughly a little bit less than a third is directly reflected, either from the surface, could be ice, could be land masses, could be water, or by clouds in the atmosphere. And the rest is then absorbed, or like parts are absorbed by the surface, thereby contributing to heating our planet. What is not reflected must go somewhere. Energy is never lost, something that my physics teacher liked to emphasize quite heavily. Then you also have emitted energy emitted by the surface. Some of this is absorbed by the atmosphere. Others is radiated back, and factoring those different parts in is essentially that what is causing global warming of our atmosphere. If you reflect and get rid of as much as we get in as output, then nothing would happen. If you get more in, you have global warming. And the problem with not that the sun is getting hotter or that we are emitting more infrared radiation from our planet, it's the problem that more of this stuff is getting stuck in our atmosphere. And a major component of this phenomena are so-called greenhouse gases, like CO2 as the most prominent greenhouse gases, but also methane and other greenhouse gases. We'll get to that in a second. So I highly encourage you to have a look. It's probably going to take you 3 or 2 minutes, but please have a look, read through it yourself, maybe also check the source that elaborates on this concept a little bit more. It's quite useful to understand that concept. Next, before we go to the greenhouse gases, let's have a look at how global warming is perceived or can be illustrated on a larger time scale. So each of those stripes here represents 1 year where we took the average temperature of our planet, and then compared it to the annual, so essentially where we took the annual mean global temperature and then color coded it according to a scheme where very dark blue colors represent cooler years, so where it's getting cooler, and red indicates where it's got warmer and warmer and warmer. And as you can see, if we start in the 1850s, so pre-industrial age, there was something that we would now perceive as very cold. So not so much global warming, but rather not that hot. But as you can see, there is a strong accumulation and clustering of very hot years towards the end of this figure. And this is essentially where we first started to witness the real life events or the real life occurrence of warmer years accumulating and essentially being witnessed by us as society and humanity. So there are different ways of illustrating that it's getting warmer and warmer. You could also just take a two-dimensional graph and say, this was the annual mean temperature in 1850, this is it now, and you can draw a line that says, oh, look, it's getting more. But this is just like a more visual way of illustrating it using colors. So what are greenhouse gases now? Greenhouse gases are those gaseous constituents of the atmosphere, both natural and anthropogenic, so both like stuff that happens due to nature, but also due to us, that absorb and emit radiation at a specific wavelength within the spectrum of terrestrial radiation emitted by Earth's surface, the atmosphere itself, and by clouds. And this property causes the greenhouse effect. So what I already explained in very simple layman terms, the more greenhouse gases are in the atmosphere, the more of the radiation is essentially trapped within our atmosphere, which then fosters global warming. And what are the most relevant greenhouse gases for this phenomena? First, water vapor, carbon dioxide. I'm not going to try, I will just stick to N2O, methane and O3, and those are the primary greenhouse gases in our atmosphere. Some of them are worse than the others, but they appear in less, or they seem to occur in less amounts, so let's stick to those. But even those are not interchangeable. For example, if I'm not mistaken, methane is 25 times more potent than CO2. Something along those lines. I have to look up the exact number if you're interested, or maybe Teresa and Anand could do so. But some of them are more potent than others. So this is why we should not emit more methane than CO2. We should try to limit that as much as possible because it's way more potent. But long story short, this is why we're talking about CO2 so much, because for most of what humans are doing where they are contributing to climate change, it can be mostly measured in CO2. Of course, we're also emitting methane and all the other things, but CO2 being the primary source of man-made or mankind-made global warming. And we have emitted quite a lot since the 1850s. And there are some countries who obviously emitted more than others. If I took the Vatican or Andorra or other small countries, obviously they didn't really contribute to that mess. Other countries, especially the highly industrialized countries, caused quite a mess. I guess that's probably my very nice support team helping me out with that exact number. 28 times, thank you very much. So it's 28 times more potent than CO2. Thank you very much, my beloved support team. Back to the figure. So especially highly industrialized countries causing a lot of those CO2 emissions. Most of them, by example, by burning fossil fuels. The cement industry, a lot of people don't know that, but it's one of the main contributors of CO2 emissions. And we're building a lot of houses, and we're building a lot of streets, we're building a lot of infrastructure. And other sources might be land use and forestry, but we'll get into like where is this coming from in the rest of the lecture series. And you can see the USA, not really a big surprise. China catching up. I mean, they have 1 billion people. Same is true for India. But historically speaking, we're also very much at the top. And that contradicts a little bit this, not a little bit, this contradicts this often used arguments of we're just Germany, we're just 80 million people out of 8 billion, what can we do that has an impact on climate change? Well, historically speaking, we can do more than 1 billion Indian people. Sure, there haven't been always a billion Indian people, but historically speaking, we have caused more mess than India has done so far. And therefore, we're not only having a responsibility, but we're also having a big impact. You could also like follow up this argument with the fact that obviously the highly super tech-driven wealthy countries should probably take the lead and not those countries who can barely afford to feed all their people. So we have to push something, we have to develop something and have to take the lead on like ending this mess. But long story short, what's the point of this figure? Giving you an intuition of who caused how many cumulative CO2 emissions since the pre-industrial age, and giving you a rough idea of how much is caused by fossil fuels and cement industry and how much is caused by land use and forestry. But it's more to give you a little bit of an intuition who causes how much percentage of that mess. So we can also try to illustrate the same or similar information if we narrow it down to CO2 emissions per capita. So if we take, okay, how many people are in that country and how, on average, how much CO2 in tons per year does the average person emit there? And that also gives you some interesting insights. So very poor countries, continents or regions like Africa, Asia, and India, where you have less consumed things per capita, have a much lower CO2 footprint compared to the industry nations. And some of the leaders here might not be as expected, or might be less expected if you go back to that figure here. So the leader on this figure is the Middle East, Canada, and Saudi Arabia. I think Canada shows up in that figure, but Saudi Arabia, Middle East is not really present there because if you accumulate them or have the cumulative CO2 emissions in billions of tons, they don't really show up there. But if you think about, okay, how much resources do you need and how many CO2 emissions do you have to just keep those people living there and supporting their lifestyle, then countries from the Middle East show up heavily there because, for example, just to control all the heating there, to make sure that there is water, for example, in the driest areas on those planet. And providing that lifestyle that a lot of rich people have in those countries causes quite a lot of CO2 emissions. So this is how the Middle East and, for example, Saudi Arabia end up as that high there. Canada, a very cold country where you have to heat a lot, but also like very high-tech country, very much up on the large scale of consumerism, of course, also has a lot of CO2 emissions. And then the usual suspects, USA, China, Germany is somewhere in between. So essentially all highly industrialized nations or continents are listed there. The rough average in 2019 was 4.4 tons per year per capita. So 4.5 tons per person of CO2 emissions per year, which is way too much, even on the average level. But we'll get to that as part of your homework. So moving on to now from who emits all of these greenhouse gases, not only you as single individuals, but also we as nations, and especially the highly industrialized nations, to how this amount of emitted CO2 becomes or starts to accumulate in our atmosphere. So in a few lectures, I think, next lecture we'll also get to the so-called Keeling curve that measures the CO2 concentration in our atmosphere since, what was it, 1960s, 70s, something like that. But now first looking more or less at the CO2 concentrations over a longer cycle. So how do we Does someone know how we got the CO2 concentration in parts per million from 600,000 years ago? You're looking very focused and concentrated on your notebook now. Good, no input from the audience. You can drill some holes into glaciers. That gives you then a layer per year, and you can roughly estimate, okay, how far are you into the past, and then you can extract CO2 levels there. Yep, Tom is correct, from the ice, so from glaciers. So we're not making up those numbers. Actual scientists have come up with those numbers. And then you can see that the CO2 concentration is cycling up and down a little bit over different ice age cycles. So there's a normal fluctuation, which is also often an argument by climate change deniers, that there was always a natural fluctuation of the CO2 concentration in our atmosphere, which is absolutely true. Which has not happened yet, is what you can see at the very right part of this figure, which is where we zoomed in a little bit here in the middle, that you can see that something happened after 1750, or more precisely at some point where the Industrial Revolution took off, and then like with some minor delay, it somehow went through the roof. So from something like, let's say 275 parts per million to way beyond 400. So something has happened there. And I think we have talked about this Industrial Revolution thing before in the other slides. And this is also why we're comparing global warming to pre-industrial levels. But because before, yes, there were some man-made or mankind-made probably effects, but they were so limited that it doesn't really make sense to talk about it in that large detail. But since then, we essentially went through the roof, and we are not done yet. We still didn't stop the CO2, the increase of CO2 concentration in our atmosphere. It's still going up, despite the fact that we're claiming to do a lot of things to stop it. So, another thing that makes the greenhouse gases in our atmosphere a problem are the so-called climate feedback effects, because it's not just trapping greenhouse gases in our atmosphere, thereby trapping more heat in our atmosphere, thereby causing our planet to heat, but that there are also effects in that system, in that system, that trigger each other and thereby multiply the effects of what we have seen before. So it's not just the more CO2 or other greenhouse gases emit, the warmer it gets, but there are also further triggers that multiply those problems. And climate feedback effects are defined as processes that can either amplify or diminish, okay, fair enough, I didn't say that yet, but amplify or diminish the effects of climate forcings. A feedback that increases an initial warming is called a positive feedback. A feedback that reduces an initial warming is a negative feedback. So you can push it both ways. Unfortunately for us, most of them are positive feedbacks. And I should probably stop carrying around my water bucket because I'm wasting so much water right now. So what are positive feedback effects? Wildfires. I burn down forests. They store CO2. I emit this CO2 into the atmosphere by burning down that forest. That, in fact, causes then the atmosphere to heat, which causes higher temperature, which causes drier seasons, which causes an increase in the probability of further wildfires to occur. Another is the so-called ice albedo effect. Albedo is a measure of the diffuse reflection of solar radiation. So ice very nicely reflects radiation back to where it comes from. So the more ice I have on a certain place, the more radiation goes back. If I don't have ice, stuff gets trapped in our system. And this is why glaciers and ice on the North and South Pole are very relevant for us to limit global warming, because the less ice we have, the more heat gets trapped in our ecosystem. So you have a lot of ice on the ocean, gets reflected. What happens if there is no ice? Water very nicely absorbs a lot of heat. That warms the ocean, which again, simplified, makes it more difficult for ice to grow. That causes the ocean to warm more, which makes it even more difficult to have ice floating around. And the same is true for glaciers. The less glaciers you have, the warmer it gets, the less glaciers you have, and so on and so on. The problem even starts once water is forming on top of glaciers, because that water absorbs heat, which then in turn helps the glacier to heat and thereby to melt, so there's less glacier. You get the idea. So there's another positive feedback loop, which is what I just explained. Thawing permafrost. Permafrost being parts, for example, in Siberia that are frozen all year round. And when they start to melt, they, for example, in Siberia, release a lot of methane that is trapped in that surface, in that soil. Methane, being a very potent greenhouse gas, causes the atmosphere to heat. That, in turn, causes the permafrost to melt even more, which releases more methane, and you have another feedback loop that is pushing it, or like amplifying itself again and again and again. Warming oceans. We talked about this in the context of ice forming on warm water or not forming on warm water. Can also have effects on systems that are circulating warm and or cold water through the oceans that we have. One of the most relevant streams is the so-called Gulf Stream that somewhere happens in the Gulf of Mexico and then goes straight up to Iceland and up to Norway and is pushing a lot of warm water there. If the Gulf Stream collapses, there's probably not really a lot of fun left in Iceland, Greenland, and Norway, because then it's getting really freaking cold up there. So this is like another effect that could really cause quite some challenges in the future. And a lot of those positive feedback loops or feedback effects have the problem that once they started, they can be very difficult or even impossible to reverse. The Gulf Stream has been in trouble from an historical perspective again and again. But for our lifetime perspective, if it collapses, if that happens, we have a big problem that is not going to solve itself while we are alive or like on any meaningful time scale for humanity. And the same is true with all the other feedback loops. Once they have been triggered and once they get into a very nice jogging condition, then they will remain a problem for us for a very, very long time. It's not a time scale that we as humanity have time to deal with. And there are more of those feedback effects. One side homework that I would like to hand out now is to find a negative feedback effect. So it's not an official homework, but I would be really interested if some of you can find a negative feedback effect. There are some. I would really like to get someone who's interested to maybe bring that back to us for either the Q&A session or for next lecture. Because we're now focusing on the positive feedback effects because they are causing most of our problems right now, or which are like causing a lot of challenges for us. And there are some negative feedback effects, but they're not relevant in the sense that they are countering any of those effects in a meaningful way that we just discussed. So, and that leads us now a little bit back to carbon emissions in itself. We talked about carbon emissions in a cumulative context, but also per capita for various nations. And then just having this detour on the feedback loops to give you like one idea of what amplifies potentially these greenhouse gas emissions that we already caused, which are way too much. But now like getting back to this carbon footprint or to this carbon emissions. The carbon emissions that you are causing, or the so-called carbon emission equivalent, so because some of those things that you do not directly cause carbon emissions, but you can find an equivalent damage or an equivalent carbon emission damage caused by them, is measured in this carbon footprint. And you've probably heard of that when you have ever booked a ticket on an airplane, because nowadays a lot of airlines trying to sell you for, I don't know, 5, 10, 20 bucks a good conscious. If you just pay those 20 bucks, then we'll compensate all your carbon emissions caused by that flight to Hawaii. It's just 20 bucks, so you can afford it, and then you can travel with no bad conscience whatsoever, because you know everything will be fine. So this is probably where most of you have heard of this carbon footprint. You can also think about it in the context of driving with an internal combustion engine car versus an electric vehicle, or instead of an electric vehicle using a train or an airplane, or when you think about vegan versus meat-based diets, there's like often this carbon footprint coming up. The carbon footprint is a measure of the exclusive total amount of carbon dioxide emissions that is directly and indirectly caused by an activity or is accumulated over the life stages of a product. So you are causing carbon emissions. Products are causing carbon emissions. If you think about it, humans are also a product of nature, so you're also a product, just not a man. You're actually a man-made product. Sorry, I'll take that back. So you're a human-made product. Sorry. So like, how much carbon emissions do you cause in a given time frame or over a life stage? And who knows where the carbon footprint comes from? Did I mention it in the teaser lecture? Did you already forget it? There's some head shaking in the live audience. So any idea where it comes from? Head shaking, okay. Live stream audience, any quick guesses? Anna is correct. Oil companies. The fuckers of British Petroleum, or short BP, came up with the carbon footprint as a way of shifting the responsibility from large-ass corporate companies who make a lot of money destroying the planet to you as individuals. Because if you would just pay 20 bucks to compensate for your carbon footprint that is caused by your flight from Berlin to Hawaii, which does not even closely compensate for that carbon emissions that you caused by flying from Berlin to Hawaii. I'm getting a little bit ahead of myself here, but essentially they came up with that concept and made this tremendously great sentence here. The first step to reducing your emissions is to know where you stand. Find out your carbon footprint with our new calculator and share your pledge today. I probably don't have to emphasize that BP didn't really pledge anything, and that they are the masterminds behind blowing up the Deepwater Horizon platforms and many, many other things. And they make billions of dollars by selling you the fossil fuels that they are now trying to somehow justify with this carbon footprint and blaming you for that. And obviously, like, everyone emits carbon emissions. Like, every one of us, to just survive, emits carbon. Like, no discussion there. There are some people who emit more carbon emissions, others emit less. But the question is not really who of us emits the most, even though this is like a relevant question, because you cannot just blame corporations and companies for all of that. Because who consumes what corporations and companies produce? If you would stop consuming airplane tickets, there would be no airplane emissions left. If you would stop consuming Apple iPhones, there would no emissions caused by Apple iPhones be left. So it's like there's always a responsibility for the individual. But it's a very shady business to just shift all the responsibilities to the consumer, to the individual, and say, look, I'm British Petroleum. I really can't do anything to stop you from burning all those dead dinosaurs. So therefore, it's still justified to, first of all, be very critical with them and their greenwashing, but second of all, also ask, like, who's emitting most of the CO2? And there's a really nice list from The Guardian where they had the 100 companies who produced more than 70% of the world's greenhouse gas emissions between 1988 and 2017. Just 100 companies caused 70% of the greenhouse gas emissions in those 30 years. And guess who's on that list? This is now less dramatic than I was hoping for because my pointer is not working, but please welcome British Petroleum again. If you examine this list a little bit more closely, you will notice that all of them are in the business of burning dead dinosaurs or dinosaur-like stuff. So from China coal to Saudi Aramco, one of the most profitable companies on this planet, Gazprom, National Iranian Oil, Exxon, Coal India. So essentially everything that is somehow in the business of burning stuff is in the top 12. And they are making up a lot of that percentage, even though at place like position number 12, we're already at just 1.3%. But just think about it. One company that emit 1.3% of the global greenhouse gases in that time, or China coal with 14% being way like far ahead of everyone. So seems to be like not really the individual should take more responsibility, but rather maybe BP could also make some pledges here. So blaming individuals and denying any responsibility is a great marketing strategy that seems to work, because otherwise we would not talk about this. Why is the carbon footprint such a great measurement that everyone as an individual is probably has heard of at some point and is thinking about how can I maybe reduce my carbon footprint? Like, I'm not saying that this is bad, but it's a little bit of an unfair game to compare it, for example, to China coal with 40%. So what do we do now? One part would probably be reducing your carbon footprint by using less resources. How do you use less resources? By consuming less things that you don't really need. By not flying to Hawaii every other week. By not buying a new iPhone if you don't need one, and so on and so on. The list is quite intuitive. I don't really have to extend that too much. So we just reduce our footprint and then we're good. That would be great, but we already talked about the feedback effects. Once you trigger them, some of them become a self-sustaining system that keeps occurring. You cannot really stop it anymore. So we talked about that. For example, with the ice, once the ocean is warmed up to a certain level, it becomes more or less impossible or very difficult to form sufficient amounts of ice that have any relevant impact anymore, and then the ice is gone. And once it's gone, it's not coming back, at least not while we are here. So it's not just about reducing that, because we have to like heavily push that part. So it's not just reducing a little bit, it's about drastic changes to do something. And some companies are at least making commitments to do that. For example, Microsoft said by 2030 we'll be carbon negative, and by 2050 Microsoft will remove from the environment all the carbon the company has ever emitted, either directly or by electrical consumption, since it was founded in 1975. Sounds good. Not gonna argue with that. Like, it's a nice goal. Apple more or less made the same promise. Polestar also has, Polestar is like an electric vehicle or subsidiary of Volvo. So they're building electric vehicles. It's pretty much like Tesla, just from Volvo. And they are also committed to reduce their carbon emissions, and they want to have something like the climate neutral car. So how do you reduce the emissions throughout the whole supply chain and then also producing the car? Because all of that causes emissions. How do you like handle that? And they first thought about this very famous concept of so-called offsetting by planting trees. You might have also seen that when you book your plane ticket to Hawaii, that you can either pay $50 or that you can go straight to planting trees. But it has some limitations, as Polestar also noticed, because for all the emissions that would need to offset and to compensate, would need to plant more trees than we have space on this fucking planet. So just continuing as we're doing right now by just reducing a little bit and by avoiding any drastic changes is not going to cut it, because we're first of all emitting way too much, and the ways how we try to then compensate for emitting that are not sufficient. So like this just being like some examples, but the general like gist is we're emitting too much, so we need to drastically reduce that. And the ways on how we try to offset and compensate that right now aren't like just some drip of waters on a hot stone is, I think, the correct phrase to use here. So there are some problems. And it's not just that there's not enough space to plant all the trees. It also has some other problems, like contributing to monocultures and loss of biodiversity, because you're not planting a diverse forest there. You're just planting one tree after another, the same type, monocultures, and if something happens to them and they're gone, then there's also at some point this interest in someone logging that down and cutting down the trees, because now they have like a nice size to be assembled as in IKEA furniture. And then suddenly, this CO2 somehow slowly creeps back into the atmosphere because it's not a living tree anymore. And then you essentially somehow, find yourself back in a nice fairy tale that does not have much to do with reality anymore. So it is not just about this CO2, but no, wait, let's phrase it differently. So it is definitely a lot about CO2. And reducing that heavily and not relying on any fake greenwashing ways of offsetting it or trying to compensate for that. But it's also a completely different additional aspect here that comes into this dimension, where these companies maybe try to, on paper, to offset everything and to compensate for that and remove CO2. But most of them are just claiming that they are doing something, because it's not just about saving the CO2 or finding a way of faking statistics in such a way that they look good, because most of what they are doing is just that. Because why do you find in those companies that have that had these like very ambitious goals, why do you find in those companies products that are barely repairable? So this is like a thing from the company iFixit, and it gives you a repairability score. And among the worst repairable devices are all those companies that claim to be very much interested in your well-being and having a great future. Because they're just taking this idea of, we're reducing CO2. It's pretty much the same as you spending $20 to compensate for your flight to Hawaii. It's pretty much the same nonsense. So they're claiming to be super sustainable and being very much interested in a great future. Sustainable also in a different definition that we are using here in this lecture. And at the same time, they're building products that don't last long, that are difficult to repair, where they even implement measures to make it impossible to repair those products, which causes way more emissions and resource consumptions and environmental pollution than they can ever compensate for. And also, they have as a goal as a company to sell you as much shit as possible. So there are very much like a lot of contradictions in those claims made by companies. So it's not just about reducing your CO2 footprint, but obviously about reducing the resources that you use in general and by the damage that you cause in general. The CO2 footprint is one of those measurements that are easy to get a rough estimate for. But just trying to reduce that one number might be very satisfying, but it's not going to save this planet, because it's a multi-dimensional complex problem. And no matter what marketing is going to tell you, it's not a simple solution. This is also why this course is longer than 45 minutes, because it's not a simple problem that you can just fix in 45 minutes. And I also don't have a perfect solution. So please feel free to contribute to that problem space. So, long story short, CO2 and other greenhouse gases being a major contributor to global warming, which is like the main topic for today, climate change, global warming. But just reducing the amount of emissions is not going to cut it, because in the last lecture, we also talked about resource scarcity and environmental pollutions as two other main challenges of the 21st century that we have to get straight. Otherwise, we're done here. So, after all this doomsday talk, questions are, okay, how much time do we have left? Not until we die, but rather like to act and to do something. But even if it's too late to like do anything meaningful, then we still have to adapt to what is coming. And in order to adapt to maybe rising temperatures or rising sea levels, you probably need an idea of like, okay, where are we going? with 1.5 degree global warming, 2 degree, 3, 4, 5 degree global warming, because how do you know what to adapt for? This is, for example, one of the research directions that my research group is very much interested in. Of course, obviously, like how can we minimize environmental pollution, resource scarcity, climate change, and social unrest? But also, since we cannot stop it anymore, how can we adapt to that? So like being one of the relevant questions here. But first, how much time do we have left? And we have looked at the greenhouse gas pathways in the first introductory lecture, where we had this figure. I think we're going to get back to that in a second, where we had this like different pathways. Okay, if we emit this much CO2, then we're going to end up with 5 degrees global warming. If we emit half of that, we might end up with 1.5, and we have to stop emitting CO2 at this point. So where we had like 5, 3, 2, 1.5 degree global warming. But all of those are just estimates of various types of simulations that try to give you a rough ballpark of where we are and what to do. Like none of those are like very accurate, because we're usually talking about various gigatons of CO2. So it's not really an accurate measurement. So even your 5, 10, 20 tons of CO2 that you emit per year in the context of gigatons, they are like quite small. So it's not a very accurate science here. It's an estimate. And this is also what I would like to give you with this figure here. So we're starting in the year 2000 with 30 gigatons of CO2 emissions. And then we have some historical values until like something like 2020, where we know roughly how much CO2 we emitted. And then we have different pathways for a 1.5 degree Celsius global warming goal, depending on our remaining carbon budget. We already discussed 1.5 is probably dead. You will see now why. But what are those other curves here in that figure? Each color thinks about a different scenario with a different probability. So for example, if you want to have an 83% chance of sticking to the 1.5 degree global warming goal, we should limit our remaining carbon budget to 300 gigatons of CO2 in total. So here we had like 40 to 45 gigatons per year. That would give us roughly like 5 to 6 years left, starting in, I don't know, 2020, 2021, something like that. If we wanted 83% chance of making it to 1.5 degree. If we want to be more lenient and say, okay, 17% chance is sufficient, then we suddenly have a 900 gigaton CO2 budget, so 3 times as much. And 70% on one hand sounds okayish. We could also pick something like 50%, then we have 500 gigatons. But none of you would, I hope you're all healthy enough to not enter or go on an airplane that has a 50% chance of reaching its destination and another 50% of killing you. And this is pretty much what we're talking about here, about very, very hard times if we just rely on a 50-50 chance here. So for me personally, previously I've done skydiving. I have a very much interest in risky types of sport activities, climbing, and like a lot of other stuff that is not quite like really extending your life expectancy. But even for me, 83%, 1 out of 5 skydive jumps going wrong? No, I wouldn't jump out of an airplane. That is even like, this is a more shitty probability than you would have for base jumping, one of the sport activities that I'm also very much interested in, but has one of the highest death rates that you can think of. So even that would be way too high. A 17% death rate is not acceptable. But now we're getting to the point, like how much time do we have left, and why the 1.5 degree global warming goal is essentially dead, is we would have been required to go heavily down that path very, very soon. I mean, this is probably roughly 2030 here. So we should be on a heavy downtrend by now, which is not the case. We're still going up there. So this is why 1.5 degree global warming is dead, and we're now probably having 2 degrees global warming as the next like larger milestone here. Sure, we could go for 1.55 or 1.6 or 1.7, but in the global like understanding, 2.0 would be the next threshold to cross, or hopefully not to cross. And this might also put this quote from Greta Thunberg a little bit in perspective, and that you might have heard before in one of her speeches, where she said the popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees. This is essentially what this is referring to, but like a background that a lot of people don't necessarily have if they don't read IPCC reports on global warming and carbon budgets and how to estimate that and how to come up with some results there. So what you can take away from that figure, even though it's not the most up-to-date one, is that we should decelerate heavily, but rather we're accelerating still. Not as much as we did in the past, but we're still accelerating on a highway. And there is this famous quote of, we're experiencing a car crash in slow motion. Instead of hitting the brakes, we're flooring the gas pedal. And that is also reflected in the temperatures going up. This figure tries to separate global warming a little bit with respect to what are human and natural drivers and what are natural drivers only. So green is just this natural fluctuation that we had. Red is essentially what we are causing, and you can see that the majority is probably caused by us. Even if this is like off by 40 or 50%, there would still be a significant distinction to be made, even if those would be 40 or 50% off. So there is a cool tool, or not a tool, a nice study with a nice visualization that we linked you here as a self-study thing. Cannot include that here in the lecture because it's not CC BY compliant, but the main gist of that visualization is taking cities, places in Europe, and for example, in Germany, like Hanover, and give you a rough idea of what the climate would be like there given a certain degree of global warming. So Hanover will have something like a climate that you might be used to from the south of France, right at the Mediterranean Sea, so the Côte d'Azur. And that is not really what you're usually associating Hanover with, a nice Côte d'Azur type of weather. Obviously now we're already like very much into this global warming part, and weather extremes have started to hit even the south of France. So this like projecting a little bit back, but it's a very nice visualization. Can highly recommend you to just like have a look at this figure to get like a little bit of an idea of which places are affected in what way. And obviously it's not just that all German cities now have the climate as south of France. It very much depends also on various other factors. Like my home city, Rostock, located at the Baltic Sea, has like a huge sea right next to it, which impacts the climate, while Hanover might have a small lake next to it, but it's not as big as the Baltic Sea and therefore not influencing the climate there as much. So it's a multi-dimensional, multi-parameter problem, but please have fun and have a look at the figure. So we've seen that figure before in the introduction. Now you might understand it a little bit better, given the background and the knowledge that we accumulated today. So what are greenhouse gases? What is causing global warming? And the different pathways of CO2 emissions, which then connect to how much the Earth's surface is probably going to warm. And here we had like the 1.5 degree goal, the 2 degrees. And as we already stated before, right now we're heading towards something like 2.8 or 3.2 degree global warming so far. We also have talked about that quote. This is just a reminder for you. But what now is essentially just the rest of the lecture is a collection of examples from the IPCC report and some other sources. I think we linked most of them down below here. And they are supposed to give you a little bit of intuition what the difference is between 1 degree global warming, 1.5, 2, 3, 4, 5 degrees, to understand better why it's rather a big deal to not go beyond 2, 3, 4, 5 degrees and not just give up. Because even if we cannot stop it anymore, and even if we already crossed 1.5, there's still a huge incentive to mitigate this problem as much as we can, and also think about ways on how to adapt and what we can adapt to, because it doesn't really make sense. We discussed this idea of just building a higher dam to combat sea level rises all the time. So what are the fights worth fighting? And what are the problems that we have to deal with? And let's first talk about heat waves. So a 1 in 50 year extreme heat wave is supposed to happen once every 50 years at 0 degree global warming. So what we had in the pre-industrial, not area, pre-industrial times. Just 1 degree global warming, which is not true anymore. I did not update that yet because I did not get a new number there. At 1 degree global warming, we suddenly have almost 5 extreme heat events every 50 years. So essentially once every 10 years. If we go up to 2 degrees, which is what we're currently looking at, we're suddenly at 14 heat waves every 50 years. And if we're going up to 4 degrees, then essentially we could more or less declare it's not just every second year, it's almost every year we would have an extreme heat wave. So there is a major difference between 2 and 4 degrees global warming. To just give you one extreme example here from Australia, in January 2020, we're at Sydney's hottest January on record so far. I didn't check if this year was hotter. I did not check for 2023. This is numbers from 2022. Where on the 4th of January, they had 50 degrees Celsius. And the number of days hotter than 35 degrees based on a 3 degree global warming would look like this. So if you compare it to now. So this is like happening at roughly 1 to 1.5 degrees global warming, 50 degrees in January. And in Sydney, you would have 11 days. Wait, no, I have to read the figure. Number of days hotter than 35 based on 3 compared to now. Okay, yeah. So in Sydney, if we have 3 degrees global warming instead of just 1, as we have it now, we would have 11 days per year instead of 31 days. Now you could say, yeah, okay, that's hot and uncomfortable, but I will just turn on the climate control and that should be fine. 3.1 days, sorry, yeah, thank you very much. That's not that bad. You still have to account for the fact that this just says at least 35 degrees hot. It could also be 50 or something else. There are other places like Melbourne that would go up to 24 instead of 11 days. Or Darwin, which would go up to 265 days per year, where we would have more than 35 degrees Celsius instead of just having 11 days. Does it really make sense to fight that, or should we just give up Darwin? Risking now that I have a lot of negative comments on our YouTube videos now from Darwin. But you get the idea, because in order to keep this a habitable zone, you would need a lot of resources. Mostly energy to probably cool all that stuff down. I mean, this is more or less Saudi Arabia or like the Middle East or the desert. This is not a livable condition. If we already had 50 degrees down there, and this is just getting worse, this is just not livable. We would need a lot of tech and resources to keep this in a habitable place, and is it worth it, is essentially the question. Like, how do we adapt to that? Another dimension to be measured could be biodiversity in the context of coral reefs, one of the places where a lot of biodiversity accumulates. So at 1.5 degree global warming, so something that we have now, 70 to 90% of the coral reefs will die off worldwide. Just adding half a degree, and we're almost done with all our coral reefs. I think I did not really add 3 degrees or 4 degrees, because what else should I add there? Nothing. So just this half degree makes huge difference. You also talked about rain and droughts before in the introductory sessions. So let's have a look at that. So I already mentioned that we have places where more rain will happen, others will experience less rain, and that we also have spaces where those will fluctuate heavily. We will have droughts and then suddenly major rain events. So at 1.5 degree global warming, 70% of land will face extreme rainfall, and average rainfall will increase by 2%. Average rainfall might be quite nice because then you don't have to water your plants that often anymore. The extreme rainfall events are slightly more annoying because usually they destroy on the farmable land what you've just grown there because it washes away, or you have the risks of landslides, floods like in the Ahrtal, so they are more annoying. At 2 degrees, this percentage doubles. So you have 36% of extreme rainfalls, and the average rain increases by 4%. Half a degree of warming would double the effects, essentially. And this is what we're heading for right now. So one other thing to prepare for is extreme rainfall events. And this is something that people living in Goslar, but also the people in Wolfenbüttel and Braunschweig, because you are living downstream from the Oker, need to think about. We have huge dam systems here to collect water, but they are made for, or they are sized according to needs and requirements that won't be true anymore in the future. So we had this like happening already in the US, that there was first there was a drought, and then there was suddenly so much water that various dams failed because there was just too much water and the water just dropped over the dam because it wasn't accustomed to the amount of water that was coming in there in a very short time period. And this is like a problem with extreme rainfall events, that sometimes you have way too much and you cannot handle it, and then suddenly you have a drought. So from too much rain at various times to droughts now. The average drought length globally, we're going to look at more specific places in a second, is at 1.5 degree, roughly 2 months. And it will just increase to 4 months by 2 degrees, and 3 degrees, we have 10 months. So it's already quite a problem because we're talking about the average here. That means some places will have much more. Now let's have a more closer look at specific regions here. So more specifically Europe, where the report gives us input for Eastern, Northern, Southern, and Western Europe. So you can see that in Eastern Europe, it more or less doubles. Half a degree to 2 degrees it doubles, and then with another degree it doubles again. Northern Europe doesn't seem to suffer so much given the constraints, and this is now a very good example to emphasize this. Those are all simulations that work under certain constraints and assumptions. An assumption that could have a heavy influence on this estimation is, for example, what happens to the Gulf Stream. If all of those estimates are still true, if the Gulf Stream collapses, it's questionable and would probably have a severe impact on Northern Europe. And I don't know if it's going for bad, like for worse or for the better. I cannot tell you because I'm not an expert on the Gulf Stream and what it could cause. There's actually very little easily accessible scientific literature on that question, how life would change for us in Europe, more specifically if the Gulf Stream collapses. Not sure if this is not widely researched, or if I'm just too stupid to find proper material on that, or if it's just like it's too difficult to predict, don't know. There is some research that deals with that topic, but you don't get like easy answers from those reports. But just using this now as an example to highlight that this is built on various assumptions that still have to hold, but you cannot factor in everything because then you get a too diverse set of results. You might get this when you start coding your own simulations as part of your study program. If you factor in too many parameters that vary too much, then you essentially get a global I don't know answer. And this is probably what you're not looking for if you want to make those kinds of estimates. Southern Europe is not going to benefit from these droughts and caused by more global warming, and Western Europe is somewhere in between. Europe is probably doing quite great. Other places, like for example North Africa, which is right now also already not really the place where you expect most of the rain, will have some more problems, which then again raises the question, how do we adapt to that? Do we try to keep these habitable places, or will people migrate away from that? I mean, we already have mass migration from various parts of the planet towards more habitable and more comfy zones. How is this going to be affected if we have 60 months, 5 years of droughts there? In average, this is the average. It could be much longer. So does it make sense to still keep this as a place habitable? How many resources, how much energy, how much time and stuff do we need to put in that? Or how do we adapt as a society to this? Because I guess most of you are not really willing to say, look, let's keep all of them there and let them die. This seems to be a morally and ethically not quite right decision. Or at least a very challenging debate that will follow if you bring up this topic. So the question is, like, what do we do before that happens? How do we adapt to this in a predictive manner and not just when the problem occurs? Because this is what we tend to do. Another measurement could be population exposed to water scarcity. Right now it's roughly like 270 million. That increases with each degree global warming, which again brings us back to the resource scarcity and resource wars. Then we also can look at this problem from the economic perspective, which is something that is often neglected. Because on one hand, a disaster can be a really good opportunity to boost the economy, because what has been destroyed before boosts the economy when it's rebuilt, because then a lot of things will be consumed again that haven't been accounted for before. But obviously, the more extreme weather events you have, it will at some point impact your GDP. That should even make the economists sad. So with 1.5 degree global warming, GDP will go down by 8% in 2100, with 2 degrees, 30%, and the damages will pile up. And at some point, you have to ask yourself, okay, can we rebuild all those damages? Or once again, choose your fights. What do we do? How do we adapt? Which fights do we want to fight? You can also break that down to specific regions. Here we're looking at the increase of economic damages from river floodings in Europe, specifically for some countries. Sorry. Most countries don't really benefit from those river floodings becoming more common. And there is a weird drop for 2% for 2 degrees global warming in Hungary. I cannot really explain that, to be honest. I would just think my takeaway from that would still be it goes up 2,500%, which is still a lot. Why it's just 2.5 instead of 4,000 doesn't seem to be the most relevant question here. But if someone has an idea, or if someone is very well versed and has an inside knowledge into the river flooding research topic of Hungary, please enlighten us. I just don't know, but I also don't have time to go into that topic. So you get the idea, you get the gist of what I'm trying to tell you. So in best case, a century of rising emissions should end before 2025 to keep global warming or global heating under 1.5 degree, beyond which severe impacts will increase further and hurting billions of people. I hope I made that point using some of those indicators. And if you go to the sources that we provided you there, you can find hundreds of more examples. Those were just those that we can easily explain very nicely now in just a few words, and that are quite intuitive. Of course, you can use more complex examples, and there are so many more examples on how this might not make our place more livable. Yeah, so 2025, not sure. No, I forgot to update that, or did we update that? How much time do we have to do 2024? Not 20 months left anymore. We have 30 months left, so hurry up. So this is from last semester. Sorry, we have to update that. I think Teresa is already taking a note. 13 months left. So now once again get why the 1.5 degree global warming goal seems to be gone. So after this very motivating, heartwarming, optimistic lecture, what's the main gist, what's the takeaway, what's the take-home message from this lecture? So talking about the basic concepts and definition of climate change or global warming related concepts. First, we talked about what's weather, what are weather conditions, what's climate change, how does climate change in a simplified concept work, greenhouse gas effect, heat being trapped in the atmosphere by so-called greenhouse gases. What are greenhouse gases? Some greenhouse gases are worse than others, feedback effects, and then we also looked at various examples on how the global warming pathways could have an impact on your very personal life, and then not really following up with the intuition of or the implication of which fights to fight, but getting at least an idea that we probably cannot just keep all the places that we have right now as it is, because that would probably even strain our resource budget even more, because it's already quite limited, as we discussed in the resource scarcity context. So what the IPCC is will be a topic for the next week or in 2 weeks. I'm not quite sure what the next lecture is, but it's a very good assessment report provided by the UN on a regular basis. And there's a very short version, there is a medium long version, and then there's a super long and super detailed version. You can check out the link to go there, and there will also find a lot of the examples that we used here in this lecture, and then a few more links with some context here, but also something entertaining. So if you like John Oliver and would like to have a look at environmental racism, have fun. It's comedy. Please keep that in mind. This is supposed to give you a little bit of more relaxed content once you're done with this lecture context. So the only thing left to do is give you your next exercise, which is going to be exercise number 2, and which is quite simple. What's your carbon footprint? Please calculate your carbon footprint as honest as possible. Submit your results, and see you again next week. We'll make a 5-minute break, and then we're going to meet again. So if this clock is correctly, then I would say we meet 10 minutes before 3 p.m. again. Thank you very much for joining, and see you in a few minutes.